Okay, so the question is find the number of non-negative integer triplets a, b and c such that a plus b plus c is equal to 10. Now this is somewhat different from the problems we have seen so far, that we are not asked to solve a particular equation as such. We want to solve, or we want to find the number of ways in which something can be done. So this is a branch of mathematics we call combinatorics, which deals with number of ways in which certain resources or certain objects can be divided among certain people. Here you can think of it as there are 10 resources, you want to distribute them between 3 people a, b and c such that everybody gets a non-negative amount of resource. Or there are many natural problems that you can address if you know how to solve these kind of problems. So it's an important tool to be aware of. So we are going to take two approaches to solve this problem. In this particular problem, we can, because the numbers are small, we can solve it using a brute force approach, and then we are also going to look at a proper combinatorial approach to solve this. So let's start. Right, so before we jump into the problem directly, a plus b plus c is equal to 10, let's first find out if there is a simpler problem that we can solve. So let's find out number of non-negative solution to let's say a plus b is equal to 10. That's all. There is no c right now, or you can think that c is frozen to 0. So if I were to tabulate the solutions, then the solutions could be here. I could say a is 0, b is 10, a is 1, b is 9, all the way to a is 10 and b is 0. So there are 11 solutions here. And it's not difficult to convince yourself that if I have a plus b is equal to some constant k now, then number of solutions, number of non-negative solutions is k plus 1. This is straightforward because it's just a table. So what we want now is number of solutions to a plus b plus c is equal to 10. We can solve it for two variables. As I said, it comes out to be k plus 1. But can we identify a pattern here? So let's see. So a plus b plus c is equal to 10. This is the equation we want to investigate. So now let's freeze c equal to 0 to begin with. C has to be equal to something. C has to be equal to 0, 1, 2, 3, something all the way up to 10. So then I need to solve a plus b is equal to, what is this, 10 minus c, which is 10. So the number of solutions here is 11. Number of solutions is 11. Now freeze c is equal to 1. So then I want a plus b is equal to 10 minus c, which is 9. So number of solutions is 10. 9 plus 1, that's k plus 1, that's our formula. So all the way, if I look at c up to c is equal to 10, so I want a plus b is equal to 10 minus c, which is 10 minus 10, which is 0. So the number of solutions is 0 plus 1, and also intuitively it makes sense that a equal to 0 and b is equal to 0 are the only possibilities here. Number of solutions is equal to 1. So total number of solutions, because c has to be equal to something, c has to be either 0 or 1 or something all the way up to 10. So total number of solutions, total number of solutions is equal to 11 plus 10 plus 9 all the way up to plus 1, which is, because we know from a previous video, the formula for adding the first n natural numbers is n times n plus 1 divided by 2. Here n is equal to 11. So this comes out to be 11 times 11 plus 1, which is 12, divided by 2. This is 6. So this is 66. So that solves the problem as stated right now. But this method looks a little cumbersome because for various reasons. So the numbers are small, so we could identify a pattern, we could do a slight brute force approach here and we could solve this. But if I were to change the numbers, if I were to make it larger, let's say a plus b plus c plus d plus e plus f is equal to 2000, then solving that using this kind of an approach would be slow and error prone. And the complication there would be that you will not be adding just a simple arithmetic progression here, 1 plus 2 plus 3 plus all the way to whatever 10 or 2000 or whatever. You will need to sum up higher powers, and adding up higher powers, well, there are ways to do it, but again it's more complex, and you will need to know the formula for adding, say, squares or cubes or fourth powers, and those formulas tend to get complicated. And say, for example, if I want to add let's say sum of 10 variables is equal to 5000, then it is not easy to come up with correct formulas for these. I mean, if you want to do it from scratch, then this is not the approach. You will have to look up the formula somewhere, and then you will have to trust that formula. So it's not an extendable approach. That's what I'm trying to convince you, that this approach will work for small number of variables and actually small number of possibilities here. But so let's find out if there is another approach, and that's where this powerful technique of combinatorics comes into play. So now again I want to solve the same problem. A plus b plus c is equal to 10. That's the solution. That's the problem we want to solve. We know the answer already, that it's 66, but let's see what is the approach to solve it. So let's take a step back. What do we want? We want, let's say I have 10 balls that I want to distribute among 3 bins. So there are these 3 bins here. Let's call them bin A, bin B, and bin C. This is A, B, and C. And one possibility could be I put 3 balls here, I put 4 balls here, I put 3 balls here. That's what I want to do. So this is one possible distribution of balls into these bins. And it's easy to see, well, I'm glossing over some of the details here, but that there is a bijection, or there is a one-to-one correspondence between a solution to a plus b plus c is equal to 10 and a distribution of balls among these 3 labeled bins A, B, and C. It's that because that's what a solution would represent, the number of balls in each bin. So let's draw this here. So I have these 10 balls, and I want to divide them among bins. So I line the balls in whatever order. It doesn't matter. The ordering of the balls are all identical, but the bins are what is different. And let's say I draw 2 vertical lines here, this and this. So then an arrangement of balls and bins like this corresponds to an arrangement of balls in these 3 bins. Basically, these 2 limiting lines define what is the number of balls in that bin. And note that it can also be 0. Say, for example, if I have this kind of an arrangement. So suppose I want a solution where b is equal to 0. So this solution corresponds to a is equal to 3, b is equal to 4, c is equal to 3. This is a, b, c. So now I want a solution where, so let's say a is equal to 3, b is equal to 0, and c is equal to 7. Then this is a is equal to 3, this is b is equal to 0, and this is c is equal to 7. Is equal to 3, b is equal to 0, or rather c is equal to 7. So this is a fairly general arrangement of balls and these sticks here. So what is the way of, but again I have just created this it's like I have rephrased the problem. I have not really solved anything here. So how do you solve something like this? So one way, or I mean, this is the combinatorial technique, that the way to solve this problem is, let's say suppose I have these not 10 but 12 balls. You will see in a minute why it is 12. This is 1 2 3 4 5 6 7 8 9 10 11 12. These are 12 balls, and I'm going to select 2 of these balls and make them into sticks. So let's say I make this ball into a stick and I make this ball into a stick. So we started with 12 balls and we converted 2 of the balls into sticks now. So now I have 10 real balls remaining. So this is a is equal to 3, b is equal to 4, c is equal to 3. Now we are in business, because Now any such arrangement of 12 balls where I'm picking two of the balls into and make them into sticks corresponds to a solution to the original problem where the bucketing or the partitioning lends itself into the solution of A, B and C, where and now you will see why it is 12, because I added the two sticks that I had as sticks. I made them into balls, I arranged the balls, and I'm now going to make those two into sticks. So that's what this is. So now the question is simple. So question is, how many ways can I select two balls out of 12 and make them into sticks and whatever? Make them into sticks and the rest of the process. But this problem is classic combinatorics problem. How many ways are there that I can select two balls out of 12? So the balls are numbered 1 to 12. I mean, as you can see here, 1 2 3 4. There is no loss of generality. I can number the balls. The identity of the balls is not important, so I can number them. So how many ways can I select two balls out of 12? So that is 12C2. 12 choose 2, which is 12C2, which is 12 into 11 divided by 2, which is again 66. I'm going to explain this formula and I'm going to give you more details on what this means. But so this formula, this is the standard notation. This is pronounced as 12 choose 2. So this is the number of ways of selecting two balls out of 12 or two objects out of 12 objects. These objects are in our example, this is 10 balls plus we needed 3 bins, so that those are the two separators. So that's why this is 12, and we are selecting the separators here, which is 2. So now this problem can be and okay, so let me also tell you the formula here. So n choose k comes out to be n factorial divided by k factorial times n minus k factorial, where n factorial is equal to 1 times 2 times 3 all the way up to n. This is the product of the first n numbers, where we can formally show, or you can take it for my word here, that 0 factorial is equal to 1. So this is number of ways of selecting k objects out of n. So this formula is important. This n choose k is n factorial divided by k factorial n minus k factorial. This is the combinatorics formula. You can look up on Wikipedia how do you prove this formula, or the proof is not difficult, but that's not the point of this video. The point is to show you how these problems can be translated into selection problems, and that's what we have here. So that's n choose k, and that's why this 12 choose 2 is our solution. So now I'm going to extend this. So we talked about, so suppose I want a plus b plus c plus d plus e plus f is equal to what? I forgot the number I chose, maybe 1000. Now using brute force here is beyond any discussion. It just cannot be done. There's no point doing any brute force solution here. But the way to solve this problem would be, so again I have 1005 balls here, because I want, let's say, a b c d e f, these are my bins, and I want to put a number of balls here in each bin. Some of the bins can have 0 balls. Sorry. And so I want a number of solutions here, where a plus b plus c plus d plus e plus f is 1000. So I have 1005 choose 5. That's the number of separators I will need. I'll need 5 separators. And in our balls and bins example, again I'm going to add the number of separators, which is number of variables minus 1, to the number of balls, and so this comes out to be 1005. I'm going to show you one nice trick here. Using the formula, it will be this 5 factorial times 1000 factorial in the denominator. So this comes out to be 1005 times 1004 times 1003 times 1002, just bear with me, times 1001 times 1000 factorial, right? So this 1000 factorial can be cancelled with the denominator, times 5 factorial times 1000 factorial. So you don't need to actually calculate 1000 factorial, which is again a massive number, but you can just cancel it like this. So that's the trick. You don't need to calculate all these factorials. You can just divide basically up to the factorial of the smaller number. So this is 1005 times 1004 times 1003 times 1002 times 1001 divided by 5 factorial, which is 5 times 4 times 3 times 2 times 1. You can cancel factors, or you can do this simple. This is the actual number is not important, but the method is important. So that's about it. That's how we solve these kind of combinatorics problems, where so let me ask a slight variation of this problem and see, maybe you can do this easily. Maybe you can, maybe you cannot. Let's see. It may not be easy. It is easy once you know the trick. So we talked about the number of ways of solving a plus b plus c is equal to 10, where a, b, c are non-negative. What if I change this to say that a plus b plus c equal to 10, but I want solutions in positive integers. I will not allow for 0. So let's see if we can do this. I mean, I'm not going to solve it right now. Think about it. So want number of solutions. Let's pick slightly bigger numbers so that brute force is not possible. Of let's say a plus b plus c plus d plus e is equal to 200, where a, b, c, d, e are greater than 0 integers. Think about this. You can solve it. Let us know in the comments, and then I'll discuss it maybe in a week or so. All right. Thank you.